Okay, this time I'm going to go over another short manuscript called Can Intensity Modulation of the Auditory Response Explain Intensity-Decrement Mismatch Negativity, published in the journal Neuroscience Letters, volume 764 in 2021. The data from this study came from the ERP core, which is an open data set created by Emily Kappelman et al., published in 2021 in the journal Neuroimage. Their database contained 40 subjects, but in this study, I just used the MMN dataset, and they recommended removing one of the subjects because they had many artifacts in their EEG data. In their MMN experiment, they used an intensity-decrement oddball paradigm to evoke MMN. And in this paradigm, there were standard stimuli, which were 80 decibels, and deviant stimuli, which were 70 decibels. And in their paper, they recommended a standardized approach to analyzing the data from this experiment. And from all other MMN experiments, they recommended channel FCZ and measurement across 125 to 225 milliseconds to analyze the MMN component. So this is part of the second figure in the paper. On the top, we've got an excerpt from the paradigm. So these squares represent different stimuli. The ones at the top were 80 decibels, the ones at the bottom were 70 decibels, and this is plotted across time. So you can see that maybe within 2 seconds, we've got 1, 2, 3.5 maybe stimuli per 2 seconds. Here, usually the ones that are 80 decibels are all considered the same, right, standards. But I figured it might be interesting to compare 80 decibel standards, which followed 80 decibel standards, and 70 decibel deviance, which followed 80 decibel standards, and then a third category, the 80 decibel standards, which followed 70 decibel deviance. And what this is intended to reflect are the differences in sound intensity transitions, or sound level transitions. Like we've got a falling transition and a rising sound level transition, represented by the blue and the green, whereas the red is like just a stable or repeated level, right? So no change in the level. Apart from, of course, the silent period, the interstimulus interval between sounds. Okay, so we've got three categories here to analyze. And at the bottom, you can see the ERPs plotted in white and the individual subject ERPs shown in red. Sorry, the white shows the grand average from the whole group, whereas the colored lines show the waveforms from each, the ERP waveforms from each individual subject. And we'll analyze the grand averages just shortly, but from what you can see of this, it should be apparent that the amplitudes in the green condition appear larger than the blue condition, and also larger than the red condition. Just at the general first glance, right, just the eye check, you should be able to see that these amplitudes are higher than these, and the blue ones are definitely smaller, right? Smaller, lower amplitudes. Okay, so the top left here, we've got plotted the grand averages, the ones that were white in the previous slide, and they're plotted with the standard error of the mean. And when we compare them beside each other, we can see here that the 70 decibel deviant produces this feature in the waveform, which definitely stands out, right? This stands out. But if we can also compare the the rising sound level transition in the green with the constant sound level in red, and see that the green waveform shows a higher amplitude across the same window. Basically, now this is not as pronounced as the blue decrease, but we could imagine if we had a 90 decibel sound, perhaps that would produce a more positive amplitude here. That's all speculative because in this experiment, there wasn't a louder deviant. So we can only compare the quieter deviant with the standard, or we can look at these sound intensity level transitions to try and estimate what might happen if we had a 90 decibel sound. Maybe it would go up like this. So from ANOVA, we found a statistically significant difference across these time windows. And then when we plotted them, the difference waveforms produced by subtracting the lower intensity deviant from the repeated standard, or the standard that followed the deviant minus the standard that followed the standard, we can see that both difference waveforms show significant differences from zero. Oops. Okay, jumping ahead there. But yes, admittedly, the intensity decrement deviant does produce this very pronounced negative peak here at the latency that we would expect to see mismatch negativity. But also the rising intensity transition produces an opposite polarity, significant increase in amplitude there. So again, we can only speculate what the resulting waveforms would be like if we had a 90 decibel deviant condition, but that wasn't included here. And when we measure the amplitudes from 1.25 or 125 to 225 milliseconds, when we measure that window, the mean amplitude within that window, and plot them, the lower intensity deviant does produce a significantly lower mean amplitude than the standard, but also the rising sound level transition produces a significantly greater amplitude as well. So these two tend to produce the opposite direction response, which suggests that the mismatch negativity latency range is also affected by other factors, these sound level transitions and the physical properties of stimuli and recent history of stimuli. So the highlights from this paper were that stimuli in the intensity decrement oddball paradigm can be separated and categorized based on sound level transitions. And these had an influence on auditory evoked response amplitudes based on having a rising sound level transition or a falling sound level transition or a constant sound level. And these tended to modulate the auditory response in opposite directions for rising and falling sound level transitions. And these affect amplitudes within the latency range of mismatch negativity. So that's another confounding factor for mismatch negativity that really ought to be dealt with in future studies. If you'd like to learn more, you're very welcome to read this article. And here's the DOI. You can find it online anytime. Okay, thank you.